So our next speaker is David Grynkiewicz from University of Memphis, who will speak on infinite subsets of lattice points having finite-like behavior. David, please.
Thank you very much for inviting me to this conference. Happy to be talking about this project, which is a fairly large project, so I'm only actually going to be able to talk about a very small portion of the project itself. But I will try and say hopefully something that's quite nice about that, even if we can't go into all the details about more of the rest of the project. And it concerns things involving lattices. So in mathematics, there are various different types of lattices. And when I say a lattice, I mean a discrete subgroup of d-dimensional Euclidean space. So that just means that every bounded subset of Euclidean space only has a finite number of lattice points. This is a fairly well-known equivalent definition to a more common definition of a lattice as being generated by linearly independent vectors inside Euclidean space. I've chosen that first definition because that property of only having a bounded set containing a finite number of lattice points is one of the key properties that gets used all the time and why I'm using lattices in the proofs. But if you're not so familiar with lattices, it's not all that crucial because the canonical example of a lattice is just the integer lattice, z raised to the dth power. And essentially, all of the lattices are isomorphic to this one. It's actually convenient in the proof to look at multiple lattices so we can take advantage of the geometry. But from the algebraic point of view, we're basically dealing with the z to the d. So let's just set some basic notation. Here I'm going to use r plus for the non-negative real numbers and z plus for the non-negative integers. And then if we have a given subset of the Euclidean space, well, there are various sets of linear combinations we can use to generate objects from the set X. For instance, if we take all linear combinations with the coefficients being from the real numbers, we get the subspace spanned by X. And if we take all the linear combinations with coefficients coming from the integers, we get the subgroup spanned by X. And if we decide we don't like the negative numbers, and we'd like to only take linear combinations using positive, non-negative real numbers, then we're going to get the convex cone generated by the subset X. So I'll be using these notations, which hopefully C for convex cone and the Z and the R in front of it to note which the linear combinations we're using. It will occur later on in this talk. And so let's start off with a fairly vague question right now. So let's say we have a subset G0 of lattice points inside d-dimensional Euclidean space. When does that subset have finite-like behavior? It's a very vague and general question, and there are probably lots of ways to interpret this, lots of ways to try and answer this question or to give answers to this question. And I'd like to basically in this talk give a little hint about one potential way of making this more precise. So to do this, we have to kind of figure what are we going to be dealing with this set. I mean, obviously, if we want a subset to have finite-like behavior, a finite set should also behave like have finite-like behavior. But we have this infinite set of lattice points. And by that key property, we know that since it's infinite, it can't be contained inside any bounded subset of the real numbers. So there have to be points that escape to affinity. They have to have unbounded magnitude and size. We want to sort of see the shape. You know, if it was all the lattice points, they would sort of escape to infinity in all possible directions. It doesn't matter what side of the set. But for a less than, if we don't have all the lattice points, there might be some directions in which the set sort of has points that sort of tend to infinity, and other directions where it doesn't. So let's make this definition here. Let's say we have a unit vector, and if we have a sequence of points, we're going to say that it's radially convergent with this unit vector as a limit, provided that if we normalize these points, they of course have to be non-zero, then those corresponding unit vectors will tend on the compact on the unit sphere to tend towards this unit vector. Of course, a compact metric space, so these such sequences are going to exist. And we have this little other condition here, which is mostly there for convenience, because we're mostly going to use this notion of radial limit to define the set G0 infinity. So we have our subset G0. In this case here, it's not inside a lattice. We can do this for an arbitrary set. And we're going to say that let all the unit vectors for which we have some unbounded radially convergent sequence of points that sort of tends towards this limit. So it's basically, we're looking at the points inside our set which escape to infinity. We're just considering a sequence of points that's getting larger and larger, farther and farther away from the origin. And we want it to, when we look at the projection onto the unit sphere, we want those points to converge to a single direction. And of course, by passing to subsequences, we can do this because we have to deal with a compact metric space under the sphere. And we're going to sort of view this as the directions in which the set escapes to infinity, at least the first order directions. You could sort of give a more elaborate definition, to which I unfortunately don't have much time to talk about, where you talk about second order or third order or nth order directions in which the set escapes to infinity, which are actually quite important. But to keep things simple, I'm only talking about the first order version of this question. So let's move on to something that looks slightly different at first. We'll come back to these directions in which the set escapes to infinity afterwards. Let's talk about some zero sum. So a very typical question or object involved in combinatorial number theory involves finite sequences of terms. And of course, here the sequence we mean in the combinatorial number theory sense here, different from that sequence I just used before. So it's basically a multiset, a finite multiset. So we allow the terms to have higher multiplicities. We don't care about the order. We just say that the element can occur more than once. And we're going to say that it's zero sum if all those terms that occur in the multiset or sequence, as the tradition holds, sum up to zero. And it's a minimal zero sum sequence if there's no proper non-trivial zero sum subsequence, which of course is the same thing in this setting as saying that you can't partition the sequence S into two smaller subsequences, non-trivial ones, which both sum up to zero. So here's a simple example of a sequence of terms from Z squared. Here I've written the sequence multiplicatively. So it's a multiplicative string. So the terms of the sequence are -1 with multiplicity 3. And we have this term 0, -3 with multiplicity 1, 1, 2 with multiplicity 1, and 2, 1 with multiplicity 1. And this use of a multiplicative string to represent our unordered sequence is handy, particularly later when we start seeing how this ties into some algebraic applications. But right now, all we really have is a collection of points with multiplicities living inside Z2. And if you add up the coordinates, you'll see you really do get 0. So there's one way to sort of view a zero-sum sequence. It's basically corresponds to a positive Z linear combination of these lattice points that adds up to 0. So it's a kind of positive dependence relation over the integers of these lattice points. And a minimal zero-sum sequence is a sort of a minimal positive Z linear dependence relation. And so what does it mean by minimal? Well, let's just see what happens with this minimal example we had before. It happens to be a minimal zero sum because you can check, well, here's the linear combination that sort of corresponds to the sequence. We have the element -1, 0 with multiplicity 3, the element 0, -3 with multiplicity 1, 1, 2 with multiplicity 1, 2, 1 with multiplicity 1. And if we use these as the coefficients and we add it up, we get 0. But if we reduce the size of any one of these coefficients, replace it by any smaller non-negative integer, we're not going to get 0. It has to be non-negative and it has to be strictly smaller. And if we only allow ourselves to use integers, we're not going to get another linear combination equaling 0. That's why this is a minimal zero sum over the integers. But of course, it's not really minimal if we allowed ourselves to use real numbers. We could choose, for instance, this linear combination down here where I take the multiplicities 1, 2/3, 1, and 0. 1 is less than 3, 2/3 is less than 1, 1 is less than 1, and 0 is less than 1. So we have a strictly smaller linear combination, which also adds up to 0. But we have to use real numbers to do that. So if we were looking for minimal positive real combinations that equal 0, this would not be a minimal zero sum in that sense, not over the real numbers. And there's often this case that when working with solutions or dealing with the integers, this sort of finite discrete-like behavior makes things much more difficult than when working over the real numbers where things smooth out a lot. And that is the case here. For instance, when dealing with sort of these minimal relations that add up to 0, it's quite easy to characterize what they look like. And this is done in terms of minimal positive bases. So we could say this definition that goes back to the middle of the last century. If we have a positive dimensional subspace, and then if we have a minimal cardinality subset X, such that all its non-negative real linear combinations equal the entire space, this is called a minimal positive basis free. Of course, that minimal number has to be, well, as we'll see in just a few moments, the dimension of the space plus 1. And note, this is not a minimal by inclusion. This is just strictly the minimal cardinality that is possible to span this space. So I'm not a huge fan of this name because it sort of sounds like it should involve something minimal by inclusion, but this is the name that's in use. And if you're familiar with Characterizing theorem, this is a very important but basic result from combinatorial geometry. It's closely tied to what these minimal bases look like. And basically, they have a very simple description. You simply take a subset Y of linearly independent points. When you look at their convex cone they span, that's going to be a simplicial cone. You have just two vectors in two-dimensional space. It looks like a triangle sort of going off to infinity. It's a simplicial cone. And now you just simply have to add one extra vector, which is contained inside the interior of that cone, and you change its sign. Right? And that lives in the outside or the negation of that cone. And that's exactly what these minimal positive bases look like. And that's exactly the support of any kind of minimal zero sum if we're working over the real numbers. The two are the equivalent in this case. So working over the real numbers, everything works out quite nicely. And with these definitions in mind, I can now do a fairly simplification, mostly for this talk, but to talk about the fuller details of what's going on, we'd have to have more. We don't have quite the time to get into some of the more subtle details. But this should give you the basic idea of what's going on. So let's say we have our subset G0 of lattice points. Question here? Oh, sorry about that if there's a typo. We have a subset of lattice points G0 inside this lattice. And let's look at this star condition. So we look at the set G0, and now we've sort of complete the set by adding to it all those radial infinite directions. So all those limits of points tending off to infinity as they radially approach something on the unit sphere. Let's just add those into the set so to sort of complete the set a bit more. Now let's look at all possible minimal positive bases that we can form using elements from the original set plus these infinite directions. Let's just suppose that any such set has to have the form that there's we'll say at most one element that's an infinite direction. So it has the form x1 plus possibly some b1, which is either a lattice point from the set or another infinite direction. We're not done. So let's use pi1 to denote the orthogonal projection where we mod out by the subspace spanned by that subset x1. And let's continue. So now, say we had taken arbitrary minimal positive basis satisfying the star condition, for which the B1 is actually an infinite direction. Let's mod out by that subspace generated by x1. We get a new subset of lattices in a different lattice. And let's suppose that the star condition holds for this new set, pi1 of G0. We can basically, anytime we find a new minimal positive basis, it has this form here, which I've written down in explicit conditions in terms of the preimage x2. But we don't stop there. We're going to continue to iterate this condition, continue to mod out and mod out each time we create this new subset x1, x2, x3. And of course, since each time we decrease the dimension by at least one, we can only have at most s no more than d iterations. And every time when we do this, we get the star condition. I'm going to say this set is finitary, at least in this oversimplified definition. This also gives me a way to quickly talk about the subsets that occur in the definition. So we have each of the possible sets X that can be created by this iterative construction. Where we form one minimal positive basis, we mod out by it, we get the set X1, we create a second minimal positive basis with its sort of finite part being X2, we mod out by it. We have a certain system of sets. We get a set system associated to our original set of lattice points. And we want to view the sets inside here, particularly if we do this definition a little bit more carefully, as being those sets which sort of capture the infinite directions associated to the set G0, or at least the negations of those directions, right? If we look at the very first condition here, right, that x1 is basically a finite set whose convex cone that's spanned out of the x1 is going to contain the negation of this vector v1. So negative v1 is inside the interior of that convex cone. It sort of encases that infinite direction. And if we were being a bit more careful here and actually defining this more precisely and carefully, these would correspond to higher order directions in which the set would escape to infinity. We can make this very precise And then we can sort of make this definition what it needs to be. But these sets X are basically those sets inside G0 which capture the infinite directions, the negation of these infinite directions, not just the first order directions, but also second order. We could have a sequence of points that tends to infinity from G0, and you can just think of it as it's tending to infinity, going off in the radially approaching a point on the unit circle, but it's also having, like, say, an unbounded drift in a different direction that's linearly independent from that radial direction it's approaching. And that would sort of be a second order unbounded direction. And then even if we could have a third order one too, this could be made precise, but I'm not going to deal with that too much in this talk. For the moment, just view these sets X0 as a set system associated to the original set of lattice points G0, which in some way captures all the infinite directions in which the set G escapes to. And this is, let's kind of give first some reasons why I call this a planetary set. That's nice sort of properties that sort of have some finite behavior. And the first one is that let's just call a set in the set system X. It's called irreducible if there's no proper subset which also lies inside the set system. So it's, if we look at the set system, there may actually be an infinite number of sets inside the set system X of G0, but some of them may not contain any smaller sets. It turns out you can show there are only a finite number of irreducible sets. Now, each one of these potentially infinite number of sets from this set system X of G0, it defines a lattice, because as you could be shown, I'm not doing this right here, they all have to be linearly independent. And so this linearly independent set will generate some sublattice of the original lattice points, not necessarily of the same rank. But even though there are an infinite number of choices for the sets X, the number of lattices that they define, this is also finite. Here's one that kind of ties in with the zero-sum thing, particularly for those that are studying zero-sums. It's kind of interesting. Again, when we're looking at for these zero-sum sequences, the behavior even of the minimal zero-sums can be quite more complicated. For instance, for the minimal zero-sum over the real numbers, those minimal positive bases, because it sort of consists of a linearly independent set plus one more element, there's never more than d plus one distinct elements inside that minimal positive basis. But for a minimal zero-sum, the number of distinct elements, the distinct terms that occur in that sequence can be arbitrarily large. There is no bound that occurs. You could have 2 million, 200 million. You can be arbitrarily large. And so these sequences over the integers can be quite complicated because we're not allowed to have this smoothing behavior from the real numbers. But nonetheless, there is some finite subset, assuming our set is finitary, so that if we delete all elements from that set, we will kill this zero-sum. That zero-sum must contain at least one element from that set. And here's one that's important, but probably a little bit harder to grasp the hand around right away. We can define a partial order on this set system by declaring, say we had two sets X and Y that lie inside our set system. Say X is less than Y. If the convex cone generated by Y contains that of X, and if the lattice generated by Y contains that of X. And with some work, you can show that this is also has only a finite number of minimal elements. This is kind of very similar to Dixon's theorem that sometimes is used to prove like the number of atoms is finite, except that here we don't have the setup and where this would be guaranteed necessarily. We have to use a lot of the structure here to sort of show that we have sort of a finite number of minimal generators for this set system. And one last little nice geometric consequence here I'll mention. If we have such a planetary set, we can always find one of these linearly independent subsets inside the set system. So if we look at the convex cone that it generates and then we negate it, then really every single point of our set is going to be within some uniformly bounded fixed distance from that convex cone. So these are also nice finite-like behavior properties that come from this. Admittedly, probably you might not have guessed to use that definition to begin with. But if you do use that definition, a correct one that's slightly more complicated, you can derive all these definitions and see that there's lots of nice finite-like behavior that's occurring for the sets afterwards. But you're all probably still wondering where that definition of finitary came from. Where is it just, it just sort of looks a little bit complicated and convoluted. So I want to at least give you some of the motivation for where this definition comes from and why it was quite important. For that, we have to get to be something a lot more algebraic. So as it turns out, These zero-sum sequences, well, if we have a zero-sum sequence and I've written it multiplicatively, and I can concatenate it with another zero-sum sequence, well, we get another zero-sum sequence because the sum of the first sequence is size 0, the sum of the next is size 0, and 0 plus 0 is 0. So that means when we sort of multiply sequences together, they stay a zero-sum. And that's really all a monoid is, an algebraic situation where we can sort of multiply things together, and that gives us some kind of situation where we can factorize things. And these monoids of zero-sum sequences, as I've described, are special cases of Krull monoids. And Krull monoids also include lots of important algebraic examples. For instance, Krull domains, which are the higher dimensional analogs of algebraic number fields. And it's a very important question, say even just algebraic number fields, to sort of consider factorization questions. And we well know that this fact that we can factorize the integers uniquely into a prime power decomposition is very aberrant behavior. That's not usual. That's very strange behavior. And people only sort of noticed that because they were so used to the integers, they just assumed that. And once they moved on to more broader contexts where factorization was possible, they soon discovered that this was not normal. There was lots of other situations where factorization could be much more ill-behaved. But even if we don't have unique factorization, we can still wonder, is the factorization completely wild? Are there some restrictions on what can happen for the factorization? And when trying to study factorizations, there are means to try and quantify this. And one way that's classically used is something that's called the elasticity of the monoid. And I'll put the definition here in just a moment, but the important thing is that for this very large class of algebraic monoids that include such things as Krull domains and even decompositions of modules into irreducible submodules in certain cases. You can even view the sort of the irreducible modules as being the irreducible factors and the decomposition into direct sums as being a factorization. There are lots of ways to generally interpret this that fall into this category of Krull domains. And the important thing is that such notions of factorization like the elasticity, which in some way measures whether the possibility of factorization is completely unrestricted or completely wild, or if there is some order to it, they all reduce down to a special Krull monoid. For instance, you can look at the certain special subsequences over the class group, and maybe only look at the subset of classes that contain primes. That might give you the G naught. And you can use a transfer machinery to transfer this question of whether or not the original monoid from algebraic contexts behaves nicely with respect to factorization. That corresponds to whether the subset G naught behaves nicely with respect to factorization. So you would like to know when such subsets find an elasticity. Here is the definition of elasticity, which for some of you may be familiar with, and for others, it's not so complicated. Basically, what happened is, because we have, in the case of a zero-sum sequence, a factorization is just sort of a partition of a given zero-sum sequence into a product or a minimal zero-sum sequences. And there may be lots of ways to decompose our given sequence, which is not minimal, into lots of smaller subsequences, which are minimal. And there may be a maximal number that occur in one partition and a minimal number. And the ratio between the maximal number and the minimal number is the elasticity of that zero-sum sequence. And if we take the supremo over all zero-sum sequences, we're going to get the elasticity of the monoid. So as I said before, this is one of the classical means of measuring, saying that the factorization behavior of zero-sum sequences is not completely wild. If this has finite elasticity, there's some kind of uniform global bound, which says that the size of the min factorization, the size of the max factorization, well, that ratio can't grow arbitrarily large. And so here's a characterization. So we have G naught, our subset of lattice points, and I'm going to define the set G naught diamond to be all the elements that occur inside the set system. Remember, this is the set system X of G naught is all these sets X which minimally capture the directions that X G tends to infinity. Also the higher order ones that I wasn't able to sort of properly define. And then this says that basically the set has finite elasticity precisely when there is no non-trivial positive R within your combination of elements from this diamond set equal to 0. That's it. And it can also be shown that that condition implies the set is finitary. So all those nice properties I was talking about, they hold for finite elasticity. And if you have finite elasticity, well, you can use all those properties to study the factorization behavior of G naught, and also therefore of the associated monoid that it was associated to. So if you were dealing with something with a Krull domain and that was the class group and those were the set of primes, then by studying the set over here, you could derive the corresponding properties for the Krull domain. And I'd like to point out a sort of important property here, something that's even independent of the algebraic applications. So we started off with a question about finite elasticity for the set G0. And that's something involving minimal zero sums, which involves minimal Z positive linear combinations. It's something that's very discrete. And this theorem over here reduces that to a question that's about R linear combination, the non-existence of a R linear combination for some special subset G0. And that subset G0, which is defined in terms of this special system X0, is also only defined in terms of positive R linear combinations. Of course, a more complicated object, but we only need positive R linear combinations to define it. And so one of the things this theorem here is basically doing is taking this very discrete object, this problem of determining whether the elasticity is finite or not, involving these discrete positive linear combinations over the integers, and reducing it, saying it's equivalent to a different type of problem involving only positive R linear combinations. And in the little time that I have left, I'm going to put one last slide here that's mostly for people that are familiar already with questions of factorization, because I don't want to go into all the details of defining everything here. But the elasticity is not the only way to define regularity for factorization. There are other measures that are often used inside the literature. And I've listed some of them here, like the delta set or the catenary degree, or some structure theorems for unions, some smaller higher order row K invariants. I'm not going to define these, but these are different ways that are used to measure whether or not factorization is wild or somewhat tame in different settings. And you can use the machinery, particularly all these nice properties about the subset being finitary, to show that actually finite elasticity, which is just one of these possible ways of measuring finiteness, implies basically the finiteness of all other well-studied invariants that aren't trivially infinite. So we can actually know that they say the delta set is finite, or the catenary degree is finite, or that various well-studied structure theorems for unions hold. All this holds. And well, that's really all I have time to talk right now. I'm going to have to stop. For 30 questions, I'd be happy to answer them. So thank you again.
Thank you very much, David. Are there any questions for our speaker? If not, then I thank David for a really very stimulating talk. And we now have a 30-minute break. So we come back in 30 minutes.